4. Air management techniques. To reduce the negative effects described above, vehicle designers use air management techniques. This involves smoothing out airflow paths, using aerodynamic shapes, underbody panels, and smooth transitions to reduce air separation and turbulence. Managing pressure zones, adding elements like spoilers, diffusers, and air vents to control where air moves faster and where it moves slower, thereby managing pressure. Cooling engine components, ensuring that air is directed efficiently through the engine compartment to cool critical components without causing excess turbulence or drag. 5. Application to vehicle design. For high-speed vehicles, minimizing aerodynamic lift and drag is crucial. Engineers carefully shape the body to control how air flows around the vehicle. For fuel efficiency, lowering drag means less force is needed to maintain speed, which translates to better fuel economy. 6. Summary. The passage is explaining how Bernoulli's principle and associated aerodynamic factors, like air separation, vortices, and tortuous airflow, affect a vehicle's pressure distribution, stability, and efficiency. Proper air management is critical to reduce these effects, which is why aerodynamic testing and design are essential in modern vehicles. Understanding these concepts allows engineers to shape vehicles in a way that reduces drag, prevents unwanted lift, and maximizes efficiency and stability at high speeds. What is the 1/2 in the equation pressure plus 1/2 times rho times v squared plus rho times g times h equals constant? The term 1/2 times rho times v squared in Bernoulli's equation represents the dynamic pressure associated with the motion of the fluid, air, in this case. Here's what each part means. Rho is the density of the fluid, air. V is the velocity of the fluid, air. 1/2 times rho times v squared is the kinetic energy per unit volume of the moving fluid. The reason for the 1/2 is the same as in the kinetic energy formula Ke equals 1/2 times m times v squared. It comes from the derivation of kinetic energy, where integrating force over distance gives us the factor 1/2. This accounts for the relationship between the velocity and the energy stored in a moving mass of fluid. Why does pressure drop as air moves faster over certain parts of a vehicle? This comes directly from Bernoulli's principle, which states that in a steady flow of an incompressible fluid, the total mechanical energy, pressure energy, kinetic energy, and potential energy, remains constant along a streamline. So, when the airspeed increases, like when it moves faster over the roof of a car, the kinetic energy of the air increases. But to keep the total energy constant, something else must decrease. In this case, it's the pressure. The energy that was previously in the form of pressure is converted into kinetic energy, causing the pressure to drop. Here's a simplified way to think about it. Faster air, higher velocity, equals lower pressure. Slower air, lower velocity, equals higher pressure. This pressure drop is what helps create lift in airplane wings or, in the case of cars, can cause unwanted aerodynamic lift, reducing the vehicle's stability. What is ambient pressure? Ambient pressure is simply the pressure of the surrounding environment, in this case, the pressure of the air outside the vehicle. It's the baseline pressure that exists at a given location. At sea level, the ambient pressure is typically about 101.3 kilopascals, or 1 atmosphere, atm. When we talk about the pressure dropping relative to ambient pressure, we mean that the pressure around certain parts of the vehicle is lower than the atmospheric pressure outside the vehicle. How does pressure become negative? When we say negative pressure, we don't mean that the pressure is truly below zero. What we mean is that the pressure in a specific region, like over the roof of a speeding car, is lower than the surrounding atmospheric pressure, ambient pressure. If the pressure drops enough, it can be considered negative relative to ambient pressure, meaning it's lower than the baseline pressure of the surrounding air. In aerodynamics, this is often referred to as a suction effect. Essentially, the air over a surface is moving so fast that the pressure in that region is much lower than the pressure of the still air around it. Gravity's role. The term rho times g times h in Bernoulli's equation represents the potential energy due to gravity. If you consider fluid movement at different heights, gravity causes variations in pressure. But on a car, which is mostly close to the ground, the gravitational term usually isn't significant compared to the dynamic pressure and static pressure terms. Gravity doesn't directly cause pressure to become negative. The negative pressure effect comes mainly from the velocity, kinetic energy, of the air, not from the potential energy due to gravity. However, in some situations, like a plane in a steep dive, gravity could play a more significant role by contributing to pressure differences along different parts of the object. Summary. 1. The 1/2 in Bernoulli's equation. It comes from the kinetic energy term and reflects the relationship between velocity and kinetic energy per unit volume. 2. Pressure drops as air moves faster. Faster air over certain parts of the vehicle, e.g., the roof, has higher kinetic energy. Since the total energy must stay constant, the pressure must drop to balance the equation, leading to lower pressure in high-speed airflow zones. 3. Ambient pressure. This is the surrounding atmospheric pressure, usually at 1 atm, 101.3 kilopascals at sea level. It serves as the baseline for comparing other pressures. 4. Negative pressure. Pressure becomes negative relative to ambient pressure when it's lower than the surrounding air pressure, often due to fast-moving air over surfaces, like car roofs, creating a suction effect. Gravity has a minor role here, but velocity is the main factor. What is an incompressible fluid? An incompressible fluid is a fluid whose density remains constant regardless of changes in pressure. In real life, no fluid is perfectly incompressible, but many fluids, like water and even air at low speeds, can be treated as incompressible when the changes in pressure are small enough not to significantly alter the fluid's density. For water, it's almost incompressible under normal conditions, meaning even large changes in pressure cause only a tiny change in density. For air, at low speeds, below about 100 meters per second or 223 miles per hour, the changes in pressure don't significantly affect the density, so we can assume the air behaves like an incompressible fluid. However, at higher speeds, like in supersonic flight, air becomes compressible, and its density changes more noticeably with pressure. Is the relationship between pressure and kinetic energy a law? Yes, this is a consequence of Bernoulli's principle, which itself is derived from the conservation of energy law applied to fluid flow. Bernoulli's principle, law. Bernoulli's principle states that for an incompressible, steady-flowing fluid, the sum of its pressure energy, kinetic energy, and potential energy remains constant along a streamline, a path followed by a small part of the fluid. This principle is a mathematical expression of the conservation of energy in fluid dynamics. Pressure energy plus kinetic energy plus potential energy equals constant. Mathematically, P plus 1/2 times rho times V squared plus rho times G times H equals constant, where P is the pressure. 1/2 times rho times G times H is the kinetic energy per unit volume, due to the velocity of the fluid. Rho times G times H backslash is the potential energy per unit volume, due to the height in a gravitational field. Conservation of energy. Conservation of energy is one of the most fundamental laws in physics. It states that energy cannot be created or destroyed, only transformed from one form to another. In this case, pressure energy and kinetic energy are two forms of energy that fluid particles can have. When the fluid speeds up, increasing kinetic energy, the pressure energy must decrease to keep the total energy constant. This is why as velocity increases, pressure decreases. This relationship has been experimentally tested and confirmed across many fluid systems. So, why does pressure drop with increased velocity? The pressure drop happens because of the conservation of energy. In a steady, incompressible flow, when the fluid's velocity increases, its kinetic energy increases. To keep the total energy constant, the pressure energy must decrease. This principle has been tested and validated under a wide range of conditions, making it a fundamental law of fluid dynamics. However, Bernoulli's principle has limitations. It assumes steady flow, no turbulence. It assumes incompressibility, works best for low-speed air and most liquids. It assumes there is no energy loss due to friction or viscosity. Summary. 1. Incompressible fluid, a fluid whose density doesn't change significantly with pressure. Water is nearly incompressible, while air can be treated as incompressible at low speeds. 2. Bernoulli's principle. This is derived from the conservation of energy law, stating that as airspeed increases, pressure decreases, and vice versa. It's been widely tested and proven true in fluid dynamics. 3. Pressure drop with increased velocity. This happens because the energy that was in the form of pressure is converted into kinetic energy as the fluid speeds up, maintaining total energy balance according to the conservation of energy law. Aerodynamic drag force is the resistance a vehicle encounters as it moves through the air, represented by a force acting at the vehicle's center of pressure, typically calculated using computational fluid dynamics, CFD, and verified through wind tunnel tests. The drag force, D, is calculated by D equals 1 over 2 times rho times C, D times A times V squared. Where CD is the drag coefficient, about 0.3 for modern cars. Rho is the air density. A is the frontal area of the vehicle. V is the velocity relative to the surrounding air. Drag is not dependent on vehicle weight but is proportional to the square of velocity, meaning the power required to overcome drag increases with the cube of velocity. The drag coefficient, CD, which significantly influences energy efficiency and fuel economy, is determined experimentally via wind tunnel tests or estimated from coast-down tests. It depends on how well air flows around the vehicle. Efficient flow minimizes drag by preventing static pressure buildup in front of the vehicle and reducing turbulence or wake behind it. Bernoulli's principle explains that as air speed over the vehicle increases, the local pressure decreases, which can even become negative relative to ambient air pressure. Conversely, decreased airspeed results in increased pressure. Factors such as air separation, vortices, and tortuous airflow paths, e.g., around the engine or wheel arches, also contribute to aerodynamic losses, managed through air management techniques, including cooling engine components. In racing cars, aerodynamic forces like downforce, negative lift, help improve cornering but also increase rolling resistance in straight-line driving. This effect must be balanced to ensure performance without excessive drag. When towing a trailer or using roof boxes, the combined frontal areas of both vehicle and trailer are added to estimate drag. If overestimated, performance may exceed expectations, but underestimation can lead to powertrain underperformance. In racing cars, downforce refers to the aerodynamic force that pushes the car downward as it moves through the air. This negative lift helps improve cornering ability by increasing the grip of the tires on the road, allowing the car to take turns at higher speeds without skidding. However, the downside is that downforce also increases rolling resistance, which is the friction between the tires and the road. This added resistance slows the car down during straight-line driving, reducing overall speed and efficiency. The challenge is to balance these aerodynamic forces, using just enough downforce to improve cornering without creating too much drag that hampers straight-line performance. In high-speed racing, teams aim to optimize this balance for the best performance in both corners and on straight sections of the track. When towing a trailer or using roof boxes, the frontal area, the cross-sectional area facing the oncoming air, increases, which directly impacts aerodynamic drag. To estimate the extra drag, the frontal areas of both the vehicle and the trailer or roof box are combined. If this estimate is too high, overestimated, the vehicle might perform better than expected because the drag will be lower than the calculation suggested. But if the estimate is too low, underestimated, the vehicle could struggle, especially if its powertrain, engine and drivetrain, isn't powerful enough to handle the unexpectedly high drag, leading to poor performance. I referred to the frontal area as the cross-sectional area because they are essentially the same concept in this context. The frontal area of a vehicle is the area of the vehicle's front-facing surface, the face, that the air hits as the vehicle moves forward. It's the two-dimensional outline of the vehicle from a head-on view, which is what air resistance or aerodynamic drag is primarily acting upon. In physics and aerodynamics, this frontal surface is also called a cross-sectional area, as it represents the section of the vehicle that cuts through the air. This term is often used because, conceptually, it's the slice or section of the vehicle's body that interacts with the air resistance, influencing drag. So in this case, both frontal area and cross-sectional area refer to the same thing, the part of the vehicle pushing through the air as it moves. For a complete aerodynamic analysis, air compressibility must be considered. However, Bernoulli's equation for incompressible flow offers useful insights along any streamline. V squared over 2 plus g times z plus p over rho equals constant, where v is the airflow speed relative to the vehicle, g is the gravitational constant, z is the elevation of a point above a reference plane, p is the pressure at that point, rho is the fluid, air, density. For road vehicles, the gz term, gravitational effect, can usually be ignored. Bernoulli's equation shows that when airspeed decreases, local pressure increases, and when airspeed increases, local pressure falls, potentially becoming negative. This explains phenomena like papers being sucked through an open sunroof at high speeds. Vehicle types exhibit different drag coefficients in frontal areas, affecting their overall aerodynamic drag. For example, modern passenger cars typically have a drag coefficient of 0.30, while larger vehicles like buses and trucks have higher values, leading to greater drag. There is a parallel between Bernoulli's equation and Newtonian mechanics, particularly the way velocity v is squared in both contexts. In Bernoulli's equation, the term v squares over 2 represents dynamic pressure, which is the kinetic energy per unit volume of the fluid, air in this case, as it moves relative to the vehicle. 1. Kinetic energy analogy. In Newtonian mechanics, kinetic energy is given by 1 over 2 times m times v squared, where m is the mass of the object, and v is its velocity. This formula essentially says that the kinetic energy depends on how fast something is moving, and this relationship is proportional to the square of its velocity. 2. Dynamic pressure in Bernoulli's equation. In fluid dynamics, like in Bernoulli's equation, the term v squared over 2 serves a similar role, but it's a measure of the kinetic energy density, kinetic energy per unit volume. Air has mass, and as it flows over or around a vehicle, it has kinetic energy, just like a moving object. In Bernoulli's equation, this term represents how much energy is associated with the moving air, and it's related to the pressure exerted by the airflow on the vehicle. 3. Y v squared over 2. The v squared over 2 term stems from how energy is distributed in a fluid. It comes from the derivation of Bernoulli's principle, where each term in the equation corresponds to a form of energy, kinetic, potential, and pressure energy. The factor of 1 over 2 is retained from the kinetic energy formula because, in fluid dynamics, we are still dealing with the energy associated with motion, but now applied to the moving air. 4. No mass term, m. Notice that there is no explicit mass, m term in Bernoulli's equation. Instead, density ρ takes its place. This is because Bernoulli's equation deals with fluids, like air, where mass is considered per unit volume, and density ρ accounts for that mass. In short, v squared over 2 in Bernoulli's equation represents the kinetic energy per unit mass, or dynamic pressure, of the moving fluid, analogous to how 1 over 2 times m times v squared represents kinetic energy in Newtonian mechanics. The factor of 1 over 2 comes from the fundamental derivation of kinetic energy, whether it's for a solid object or fluid in motion. It may seem a bit strange to still see the v squared over 2 term in Bernoulli's equation, but there's a clear reason for it that ties back to the concept of kinetic energy in fluid dynamics. Let me break it down further to clarify why that 2 remains in the denominator. Why v squared over 2 in Bernoulli's equation? Bernoulli's equation is derived from the work-energy principle for fluids, which closely parallels the way kinetic energy works for solid objects. The presence of v squared over 2 can be explained by the following points. 1. Kinetic energy per unit volume. In Newtonian mechanics, we know that the kinetic energy of an object is given by Ke equals 1 over 2 times m times v squared. For fluids, we are interested in the kinetic energy per unit volume of the fluid, not just the total kinetic energy. Since fluid density ρ is mass per unit volume, we can rewrite the kinetic energy in terms of density. Ke equals 1 over 2 times rho times v squared. This equation now represents the kinetic energy per unit volume of the fluid, where rho is the air density and v is the velocity of the fluid, air, relative to the vehicle. 2. Work energy principle applied to fluids. Bernoulli's equation is a statement of energy conservation along a streamline. It accounts for the kinetic energy, represented by rho v squared over 2, potential energy due to elevation, the g times z term, and pressure energy, the p over rho term. Since kinetic energy has a 1 over 2 factor in mechanics, this term appears similarly in fluid dynamics. 3. Why the factor of 2 stays in the denominator ***. The v squared over 2 term comes directly from the expression for kinetic energy. The 2 in the denominator remains because, even though Bernoulli's equation deals with fluids, the relationship between velocity and kinetic energy, which is always proportional to v squared, doesn't change. The 1 over 2 factor is intrinsic to the definition of kinetic energy, reflecting that the energy increases quadratically with speed. So, the 2 doesn't cancel out or disappear, it's a necessary part of how kinetic energy is expressed. 4. What this term represents in Bernoulli's equation. In Bernoulli's equation, v squared over 2 represents the dynamic pressure, the pressure contribution from the fluid's motion. It's an essential part of understanding how the fluid's energy is distributed between kinetic, pressure, and potential energy. The v squared over 2 in Bernoulli's equation directly parallels the kinetic energy formula in classical mechanics. The 2 in the denominator comes from the kinetic energy expression and stays there because the equation describes how the fluid's kinetic energy changes with velocity. This term is essential for capturing how fast-moving fluids, like air, exert dynamic pressure on a vehicle. In a way, it might seem like we're saying, out of 2, there is velocity squared, but the reasoning is more mathematical and conceptual than that. The v squared over 2 term in Bernoulli's equation isn't implying that velocity squared is out of 2. Rather, the 1 over 2 is a fundamental part of how kinetic energy, and by extension, dynamic pressure, is derived. Let me break this down further to clarify what this term is expressing. Why the 1 over 2 factor is present. 1. Kinetic energy definition. The kinetic energy Ke of an object is defined as Ke equals 1 over 2 times m times v squared. This formula comes from integrating the work needed to accelerate an object from rest to velocity v. The 1 over 2 emerges naturally from this process of integration. It's essentially saying that for every unit of mass, the energy increases with the square of the velocity, and the factor of 1 over 2 reflects the nature of this energy buildup. 2. Kinetic energy in fluids. In fluid dynamics, we replace the mass m with the mass per unit volume, which is the density rho of the fluid. This gives us the kinetic energy per unit volume. Kinetic energy per unit volume equals 1 over 2 times rho times v squared. This is the amount of energy stored in the moving fluid, and it's proportional to the square of the velocity. 3. In Bernoulli's equation. Bernoulli's equation is essentially an energy conservation principle applied to fluids. It tells us that along a streamline, the sum of the pressure energy, kinetic energy, and potential energy remains constant. The v squared over 2 term, multiplied by the fluid density rho, represents the dynamic pressure due to the fluid's motion. Is velocity squared out of 2? Not exactly. The v squared over 2 in Bernoulli's equation doesn't imply that velocity squared is somehow taken out of 2. Instead, it's a reflection of how energy scales with velocity. The factor 1 over 2 shows up because when you're calculating kinetic energy, the relationship between force, distance, and velocity integrates to produce this 1 over 2. In short, the v squared part reflects that energy, or dynamic pressure, grows quadratically with speed. The 1 over 2 is a factor that results from the derivation of kinetic energy and doesn't mean anything is being taken out of 2. It's just a mathematical result of how kinetic energy accumulates as speed increases. So while it might feel like velocity squared is somehow divided by 2, the v squared over 2 term is actually a direct outcome of how kinetic energy is mathematically structured. The 2 in the denominator isn't about taking velocity squared out of 2, it's simply part of the formula that captures how kinetic energy, and by extension, dynamic pressure in fluids, behaves. It is written in a way that suggests division, because it is division, but the reason for writing it this way has to do with how kinetic energy is derived and expressed mathematically.